Okay, it started recording now. Kindly restart. Thank you.
Okay, thank you, Sunil. So I was telling that uh, this course which we have designed to understand the quantum computing, starting from the basics till the end, where the present status and the present different companies, how they are making this different platform to realize the quantum computing. So this course which we have designed, I already shared you the pattern, the topics which we're going to discuss, starting from the introduction to quantum computing, a bit about the fundamentals, and I will discuss this content in detail. But what I'm trying to convey to you is that if we want to, let us say, understand this topic in a holistic way, so better that we should now sit with the one copy, one pen. This is going to be a pedagogical completely. We need to write down, note down all the points. I will not going to show you too much slides. I will stick to the board. I will I can write down everything on the board so that the speed you can match. Sometimes I feel that when we try to deliver the lecture through the slides, then there is always a time lag now between the teacher and the students. So keeping that thing in mind, I have decided to deliver this talk on the board. So that we can keep our frequency matching completely. So the first thing you have to do that, please note down, listen this lecture carefully, prepare your notes, and after 2 or 3 lectures, I will give you a first assignment. So their total will be 3 assignments I will be delivering to you. Assignments you need to solve yourself. I will provide you the solutions of the assignments, uh, and then you can cross-check whether uh, your attempts in the assignments is correct or not. So that is the one part. Then second, I have prepared 2 quizzes, and these quizzes will carry some marks. So the 2 quizzes, the date already I have given to you. So these quizzes I will going to conduct online through a Google platform or Google form. And then finally, on 12th, we will be going to have a one final test or final paper, I can say, that will also going to carry a marks. And based upon your attendance and based upon how you perform in the quizzes and in the final test, the ISAMP will provide you the corresponding scorecards and certificates. So that is the pattern I'm going to follow for the next 8 or 9 lectures, whatever we have. The timing will remain same, 6 to 8, and maybe sometime we may exceed little bit because we are trying to cover too many things. And you can understand, understanding everything within 16 hours is going to be always challenging. I will try my best to deliver uh, every, everything within that time period, but maybe some lectures may exceed maybe 10-15 minutes extra. So bear with me at that part. And we should also, I think, keep ourselves open to discuss the questions. What I can do that maybe once I finish, let us say one sub part after maybe 10 minutes or 15 minutes, I will then ask you to now open or come up with your questions. So that way we can create more coherence in the class, and we can avoid too much derailing that happens sometime frequently. So better that when I ask you to now ask the questions, maybe not more than 5 to 10 minutes, I will invite you to discuss the questions, and in that time periods we can discuss the questions. But again, please keep in mind that you have to prepare your notes, and although the video lectures will be provided to you as recorded, but better that uh, let's make it a classroom teaching. So I hope I am audible to everybody. Can maybe somebody can just give me some feedback uh, and then I think I can switch to the board and we can start.
Okay, I think some of them already messaged me saying that they can hear.
Mhm.
Everything is okay. And whenever Sugam is asking questions, you can actually unmute yourself and ask questions directly. Or you can also add chat, send questions in chat. I think it is better to be interactive by asking questions directly by unmuting yourself. This is possible.
Yes.
Okay, I think then it is better that don't interrupt in between the sessions. I mean, like anyway, because there will be some time allocated for asking questions, right? Or do you want them to interrupt in between? Or
I mean, sir, if there is something very necessary, definitely you can
very
interrupt.
necessary? Yeah, of course, yes.
But definitely
Okay,
I will allow everybody to ask question after 5 minutes or 10 minutes, definitely.
okay. That's great.
Okay.
Okay, yeah, sure.
But in between, if you feel that something is definitely required to discuss, then definitely you can interrupt in between. Okay, so let me share my screen and then I can take you on my board. Okay, so what we're going to discuss in today's class, I will be now going to discuss the content part. So the content and that will be going to be a bit introductory in nature. And here I will briefly discuss uh, starting to the end point. Okay, because I feel that it is very important to understand the content topic which we're going to discuss in the next 16 hours. And once you get whole story, then maybe it will encourage you to stick with us till the last class. So I will start with the, I mean, today in today's class, I will completely going to discuss for the next 2 hours introduction to the whole syllabus, what we're going to discuss for the next 16 hours. So the first topic we will discuss is we're going to give an overview. I mean, this whole lecture is all about overview of algorithm or quantum computing, then algorithm, programming, and hardware. So that is the today's lecture. So we will give complete overview of the quantum computing, how to go ahead with this, what are the algorithms and programming like Qiskit, and then hardwares, different hardwares like different platforms like superconducting, conducting ion qubits, photonics, etc. So in the first part, uh, from tomorrow onward, I will be more, or maybe if time permit, then I can discuss today also. I will be more going to focus about the historical development. So in the historical development, our task will be to not just have a glimpse of how the calculations evolved, or quantum computing system evolved. So maybe we can start with our first computer that was very big, and that is also known as ENIAC. And this was developed in 1946. And if you have gone through the history, you must be surprising that this was a very big system. The total area this ENIAC were using around 300 square feet. And this was completely based upon the vacuum tubes. Around 17,000 vacuum tubes were used. Similar amount of transistors, registers were used, 10,000 capacitors were used, relay, and it was weighing around 27 tons. No doubt, it is not it's not logical to compare the memory of this system, but if you compare with the present system, then the memory of this device was simply 83 bytes. And now you can imagine ki at the present time, our even single mobile going to have a gigabyte memories. So that is the first computer developed 1946. Then in the historical development, little bit we'll take a glimpse that how the first transistor was developed by the Bardeen in 1947. And after that, semiconductor never looked back. So after that, the system start getting smaller, smaller, and smaller. And now you know that there is a Moore's laws. And this law says that every second year, the number of chips or number of transistors on chip will become double. So every second year, the number of chips, it means the size of the transistors are getting smaller, smaller, and smaller. So for example, we will little bit talk about now the simple functioning of the MOSFET, where you can understand what is the problem exactly, where the issue come with the our now present computing system. So in the MOSFET, we have one source, then there is a gate, sorry, the drain, and then there is a insulator, and after that we place a gate. And for example, if this is a p-type substrate, then if you apply some voltage on the source, then depending upon the gate, for example, if you gate, let us say, put a positive potential, then this electron will going to attract here, and here then you're going to have a conducting channel, and this electron from this side easily travel to the drain. So this MOSFET is going to act like a switch when the gate voltage is positive. And when the gate voltage become negative, electrons will be repelled out. There's no conducting channels, and this is going to be then act like the off switch. Now, when I say the size of the transistors are getting smaller, smaller, and smaller, what I mean to say that this distance, the distance between the source and the drain, that is, let us call L, this is getting smaller. And at the present, you can see already a company like IBM, they have reached to the 2 nanometer. And if this thickness or this distance goes to, let us say, 1 nanometer, then you can see that at this scale, 1 nanometer scale, these electrons from the source to drain, they can easily tunnel. There is a quantum mechanical tunneling. So the separation is so small, 1 nanometer, electron from the source can directly tunnel into the source to drain without having any role of gate. So it doesn't matter whether gate is positive potential, negative potential, electrons will going to flow from the source to drain. It means at this level, this transistor is not going to work at all. It's not going to act like a switch. So this is the issue. It means these Moore's laws are no longer going to work below 1 nanometer. And this is the issue the present time the semiconductor companies are facing. After a couple of years, further miniaturization of the semiconductor technologies is going to stop completely. So what is the solution? I mean, this tunneling is a fundamental problem. You cannot solve it. It will remain. It's a fundamental limitation. So there is other problems also with this technology we will discuss when I will come to like heat dissipation also. When I talk about heat dissipation, then heat dissipations can taken care by different technology. But when talk about quantum tunneling, this is a fundamental limit. You cannot cure this issue. There is a ultimate solution for this, okay, or alternate solution, and that is the what we call as the quantum computing. So in the first section, when I say that the historical development, so here we will try to discuss this development, that how this quantum computing is going to handle. I mean, this quantum computing not going to resolve the issue of the quantum tunneling, but it is a different regime. Okay, so here you can see that we're going to use the qubit concept. We're going to use the superposition. We're going to use the entanglement. So this basic phenomena like qubit superposition entanglement, this is going to give us an alternate way to do the computing. And we will see that in this way, and of course, the quantum computer is much more superior than the classical computer. And how it is superior, we will discuss in the second part then. So this is what I'm planning to discuss in the first section, the historical development, how the uh, concept of the quantum computer came into picture and why they are more interesting at the present time. So in the second part then, now before we go to the quantum computing, we need to understand the certain basic concept. So my second part of the topic will be the certain concept of the quantum mechanics. So we will try to understand the quantum mechanics fundamentals. That is the second lecture. And what we need to understand, of course, discussing, I mean, this is only 2 hours of class or maybe 2 to 3 hours of class. And you understand that explaining the whole quantum mechanics in 2 to 3 hours is going to be very difficult, very challenging. So I'm expecting that you already having a prior knowledge of the quantum mechanics. And I will brush up a little bit and I will try to now bring your focus on certain parts, okay, which are important and which are required to understand the quantum computing. So although I will start with the very basics, I will try to explain you from the how this quantum mechanics came into picture. So maybe what we can do that here also, maybe we can little bit talk about historical experiments. I mean, I will just give a brief. I will not going to discuss in detail. Uh, but anyway, before I come to the next part, quantum mechanics fundamental, in the first part, in historical development, if anybody have any question or any comment, please let me know so that after that, I can come to the second part, which we will discuss in detail. Yes, any questions or any suggestions or any comment you want to give? It is fine. Shall we go ahead? I mean, you have to speak also. This should not be a one way of the class. I mean, we should interact. When I say that, I will not. I will. When I
It's
say,
okay.
okay. So in the quantum mechanics, then I will be discussing. Now I will start with the historical experiments, like let us say black body. No, black body radiation, and we will try to get a glimpse that why this black body spectrum now raised the questions to the present at that time the present classical mechanics, and the classical mechanics were not able to explain the black body spectrum, and then the Planck theory came into picture. So the Max Planck, he then, to explain this black body spectrum, he came up the concept that radiation or the photon, I mean, the EM radiations is not behaving like a waves, but they behaving like a particles. And this gives the dual nature of radiation. So it behaves like a wave and it will behave like a particle also. And we always say that okay, this is the birth of the quantum mechanics. But of course, this gives the initial trigger for the quantum mechanics. But actual quantum mechanics started now after the second, I mean, this is called the de Broglie hypothesis. So we will discuss a little bit, not too much detail. So de Broglie said that if the radiation can have a dual nature, if they can behave like a wave and the particle, why not matter can have a dual nature? So matter in general behaves like a particle. For example, think about electrons or protons. But the question was that why it cannot behave like a wave? Then the de Broglie came up with the concept that it can behave like a wave as well. And I will request everyone, please don't write on the board. This board is not for you, it's for me only. Maybe you can remove. Whatever you write here, I will not able to remove. It is only you can remove it. Yeah, thank you. So then de Broglie said that even matter can have a dual nature. It can behave like a particles, it can behave like a wave. And for the particle nature, there was, of course, experiments were there. For the wave nature, there was no experiment at that time. And you can see that there was a very important experiment came, that is the Davison and Germer. Okay, and Davison and Germer, they perform experiment, and the experiment they use the electron as a beam, and they incident on the nickel crystal, and they saw that this is creating a diffraction pattern. The first time it become evident that electrons can produce a diffraction, and you know that the diffraction can be only understood by the wave nature, not by a particle nature. So after the Davison-Germer experiment, it was clear that the electrons or matter definitely have a dual nature. They behave like a particle also, and they behave like a wave also. And this wave is what we call as the matter wave. So we will discuss about the matter wave. That is the third part, because this is here I want to bring your attention. This is something we need in the quantum computing. So then when the matter wave come into picture, then the question was that how this matter wave is going to look like. Okay, so when you talk about a radiation or like EM waves, so in the EM waves, there is something oscillating, and what is oscillating? Electric field and the magnetic field, which is the physical quantities which you can measure. Electric field is the volt per meter, magnetic field is Tesla. This is the physical quantity, you can measure it. But when we talk about a matter wave, so what is oscillating? At that time, nobody was knowing. Even today also, although we say that this is the probability wave, but still it is one interpretation. It is not 100% convincing. Or only not the only way to interpretation still required. Okay, what is oscillating? No one knows. Okay, so people try to understand what is oscillating. When they fail to give the physical interpretation of the matter wave or the wave function, that is called psi. Okay, then they thought that better that we should stick to the mathematical form. And for the mathematical form, then they say that better. I mean, they try to figure out how it look like, and they come to the some conclusion that it is going to behave like a wave packet for a free particle. So for a free particle, the wave function is going to behave like a wave packet. Wave packet means of like this. So that is the wave function. And mathematically, this wave function nothing but a superposition of many different waves of different frequencies or wavelength. So maybe I can call this as the phi1, this I can call it a phi2, this is a phi3, and this has the momentum, let us say, or wavelength lambda1, wavelength lambda2, lambda3, momentum p1, p2, and p3. So why I'm emphasizing here that because from here, this conclusion came into picture that the psi, the total wave function, is nothing but sum of these individual. I mean, for discrete wave function, I can say this is sum of this individual. This is what is called superposition here. So in the quantum computing, the superposition is the very essential component which we need to understand. And maybe we will use the cat notation or bra notation also. Or maybe we can say like, this is how we can write down. So the basic concept to write down psi as a linear combination of phi 1, phi 2, phi 3, this idea you can understood, it come from the wave packet. Now, similarly, in this section, then the fourth part, which I will be discussing, is the mathematical interpretation, okay, or mathematical foundation of the quantum mechanics. Mathematical foundation of quantum mechanics. And in this mathematical foundation, we will see that this phi 1, phi 2, phi 1, phi 2, phi 3, and so on. I mean, so this whole wave function, okay, we can make no, one kind of analogy with our no, linear vector space. For example, in the Euclidean space, we know that if there is a vector, let us say R, then this vector R can be written like some component, let us say A1 into I plus A2 into J. So same like here, psi written like a C1 phi 1 plus C2 and phi 2 and so on. So this is in 2 dimension. When you go in 3 dimension, this R is going to be then A1 I plus A2 J plus A3 K. So although in the Euclidean space, maximum we can go to 3 dimension in the real space. But in the general vector space, when you talk about, so vector can go for n dimensions also. So here, what is the property? That this I, J, and K, they are orthogonals. And you will see that here also the phi 1, phi 2, and phi 3, they are orthogonals. So they behave in similar way. So the way R behaves here, I can call about the psi. The way phi 1, phi 2, they behave like I and J. So I can say that this whole wave function, okay, can be treated as a vector. But this vector will going to have a space, and that is called a Hilbert space. So we will discuss here the concept of linear algebra little bit, because without understanding the linear algebra, it will not be easy for us to do the quantum computing or understand the quantum computing. So I will go in a very, a very smooth sequential manner, how the quantum mechanics arise from the black body, and then how the de Broglie said that matter wave exists, and this matter wave then can be represented for a free particle like a wave packet, and this wave packet can be written as a superposition of these phi 1, phi 2, phi 3, and these phi 1, phi 2, we will see that they are going to be orthogonals, and as a result, I can compare this psi as a vector. And from now onward, then we will call psi as a vector, or you can say not only a wave function, but you can call also as a vector, and that vectors lies in the Hilbert space. And this Hilbert space, the minimum dimension of this Hilbert space will be 2, and the maximum dimension can be infinite. Okay. So minimum dimension, for example, for a spin, and maximum dimension can be for a free particle, like a position or momentum representation. So smoothly, we will go from the wave function to the vector, and we will see how this wave function are treated like a vectors. So, and then of course, I will also discuss the notations like Dirac notations, because this is something we're going to use frequently in the quantum computing section. So after this, then I will discuss another very important concept, that is the measurement in quantum mechanics. So for example, when you talk about this wave packet, so I said that this wave packet is going to have this kind of representation for a free particle. And this is going to nothing but a superposition of large number of such monochromatic waves and so on, having, let us say, momentum P1, P2, P3. Momentum is defined, no, because this wavelength is defined for each individual waves. So momentum is defined. And let us say that this is a total wave function. And now just try to understand, if I want to measure the position, okay, so this is the, let us say, electron, a free particle. So this electron wave function, when the electron is going to behave like a particle, so of course it will have a particular presence in the space. But when this is going to behave like a matter wave, so in the matter wave, it is going to behave like this wave packet. Now, when you're going to measure the momentum of this electron or position of this electron, so in the quantum mechanics, so we will see that we're going to have a corresponding now operators. I will talk also about the operators when I will discussing here. So you can also add quantum operators and observables. So we will talk about those operators and observables. So let us say if you apply momentum operator on this wave function. So definitely, it's very simple logic that if you want to measure momentum of a particle, so when this electron is behaving, is going to act like a matter wave, okay, so it is going to have a momentum spread. Okay, so it will going to have all momentum possible from, I mean, this is not a discrete system. I have shown the discrete system, but please excuse me for this simplification. This is a continuous now variation of the wavelength and the momentum. Just for the simplicity, I am showing as a certain discrete now P1, P2, P3. But my point is that this electron will have some momentum spread. And once you're going to measure momentum, so after the measurement, you will get only one value. And that value will be either P1, P2, or P3, or maybe any other values, no, which is continuous. So for example, this phi 1, phi 2, and phi 3, they corresponding momentum is P1, P2, P3. So let us say if you get a momentum P2, it means that this information will lost. This information will be lost. Only this information will remain preserved in the system. It means earlier the psi was a superposition, okay, of phi 1 and phi 2 and so on. But after the measurement, you will either get momentum P1, P2, P3, and so on. Let us say if you're getting P2, then other information will be lost. Only this information will survive. It means this wave function is going to collapse into phi 2. And this is what is called the collapse of the wave function. And it means this P is going to operate only on the phi 2 and corresponding momentum value you will get. It means that once you're going to do the measurement, the wave function going to collapse. Before the measurement, it is going to exist in all possible values. No, it's going to have all possible momentum values, but once do the measurement, it will going to collapse. So this is the fundamental, I can say, principle in the quantum mechanics, which say what happens when we do the measurement in the quantum mechanics. The wave function going to collapse to one of the eigenstate. So here we will emphasize, because this is something again required in the quantum computing system. So these are the basic things now which I need you to focus. Okay, I will not discuss other parts like now hydrogen atom problems or particle in a box. Those things we will discussing. But my focus will be just to let you go systematically how the quantum mechanics developed from the classical mechanics, and these matter waves, de Broglie, why we write down this wave function as a superposition of the phi 1, phi 2, and what happened when you try to do some measurement. Why this wave function collapse? I mean, I don't know the why it's collapse, but the common observations say it should collapse, okay, because it should give only one particular value. So that is the second part, second lecture, which may take 2 hours, or maybe it can extend more than 2 hours, or maybe 10, 15 minutes extra I can take. But this is something very important. Maybe you can also brush up your quantum mechanics and try to focus on these particular aspects, which is more essential to understand the quantum computing. So now, if you have any question up till here, if you want to make any comment, please let me know. This is the most
Hello, sir.
important.
Hello,
Yes.
sir. Can you hear me?
Yeah.
Sir, this is Anup. I have two questions regarding the first part there. So you are choosing MOSFET, that field effect transistor, right?
Mhm.
Why you are choosing that? Because we have also some transistor they are developed built on the impact ionization, not in the field effect one. So what is the advantage and why you are
Um,
choosing that?
no, no, I am not choosing that. Actually, I was trying to explain you, okay,
Okay.
that why the present semiconductor industry is facing a problem. So I wanted to explain you that what is the meaning of no, scaling down or going down in the dimensions. So I wanted to I wanted to take the simple example of MOSFET to show
Mm-hmm.
you okay, what is the meaning of this length L, and this L is no, shrinking down, and once
Mm-hmm.
it goes to, let us say, below 2 nanometers or 1 nanometer, then this quantum tunneling phenomena will now going to now put this limitation. So
And
I'm not taking one. Of course,
mm-hmm.
I means uh, to overcome these issues, there is another issues called heating. Now,
Mm-hmm.
to overcome the heating, there are different types of materials we can use. For example, you can think about graphene-based FET, correct?
Yes.
You
And
can think about the carbon
uh,
nanotube FET, okay? But
true.
remember, even in these FETs, this quantum tunneling is not a solution.
Okay. So that regarding the relative question, this value, which is you mentioned about 1 nanometer, which is less than when
Yes.
less than two, and what are the factors this that decides this value?
Uh,
Because if you see that atoms, it will be order of Armstrong 10 to the minus 10. So when we go beyond 2 nanometer and reach 1 nanometer,
See, I mean,
then
so this
Mhm.
1 nanometer is not something very strict, okay?
Okay,
If you can increase the dielectric constant, okay,
okay,
in between, for example, here, you can see this is dielectric material, correct?
yes,
So at the moment, people generally use the silicon dioxide.
true.
And the silicon dioxide, when you compare if you take some other material, no, which is going to have a, let us say, higher dielectric constant compared to the silicon dioxide. For example,
Mm-hmm.
hafnium oxide. Okay, so hafnium oxide have a more than 20 dielectric constant. So with the more dielectric constant, actually you can increase the thickness of
Okay,
the dielectric, no, and this because the tunneling depends upon also no on the length, correct?
yes, true.
So if the length you can increase, and that can be done by increasing the dielectric constant. So
Mm-hmm.
that can now somehow give you flexibility to further go down a little bit, okay, more than one, less than 1 nanometer. But you will again going to stuck down now. Is not the ultimate
Yeah,
solution. It will give you some temporary relief, but not the
true.
ultimate solution.
In theoretically or ideally case, the tunneling will not be happen if there is an infinite potential barrier, right?
Exactly. But you
But
cannot create that one. Yeah.
yeah, true. Okay, thank you.
Yes, thank you. Anybody else want to ask from this
Yeah,
quantum mechanic?
Sugam, there seems to be some questions in the message.
Mhm,
So one question, both are related.
mhm.
Is there any reason for the wave function to collapse after measurement? Another question is, explain more about the wave function collapse. So both of them are addressing
Definitely,
the same
definitely.
question. So you can just, yeah.
Yeah. I mean, so, see, no one know why the wave function collapse. It is a still open question in the quantum mechanics. It is the only, or you can say this is the no, quantum mechanics postulates. Is a part of a postulate. Okay. This is based upon the observation. Observation, like I mentioned that key, if you, for example, think about other way around. When you say this is the wave packet of electron, So when electron behave like a particle, it's going to have some dimension, but when it's going to behave like a wave, so this wave will going to have a certain extension in the space. Let us say from x1 to x2. So if you try to say where electron is, so you can't say electron is here, here, here. Electron is everywhere from x1 to x2. But when you going to do a measurement, so after the measurement, when you're going to locate the electron, okay, so electron will be going to show its presence, maybe here, correct? Let us say. So after the measurement is no longer, this wave function no longer exists. This wave function going to collapse into a single spike, a delta function. So the whole wave function, which is written like a C1 or phi1 after the measurement. So when you do a, let us say, X measurement on the psi, it is going to give just a X naught. So this is X minus X naught. It is going to collapse to a delta function. So it is our common observation. All the now postulates of quantum mechanics, they are developed through experimental results and the observations. So this observation says, the experiment also says that the electron going to show its presence only at a one point. And it means that it simply indicates that other possibilities are gone. The other informations are gone completely. Only one information survives. So the wave function collapse. Idea come from the observation. Why collapse? Nobody knows. Only you know that, okay, what is the probability of collapsing in this state? Maybe next time when you're going to do the measurement on a similar system, maybe this collapse may happen here. Okay, only you can say the probability. Collapsing in this state, certain probability, collapsing in this state has certain probability. But don't worry, I mean, so these things I will discuss. We have a 2 hours, we have a 2 hour of time to discuss this concept. But this is a short answer for your question that no one knows why the wave function collapse. This is the postulate of quantum mechanics, and these postulates are based upon the observations and the experiments results. I hope a little bit convincing. Okay, anybody else?
Awesome.
Mhm. Okay, so if there's no question, then the third lecture, in fact, when I said 2 to 3 hours for the quantum mechanics, I will take another lecture into this part. And here we will try to understand the Stern-Gerlach experiment. Because I will be explaining the quantum computing using the spin concept completely. So for that one, can you please mute your mic? Okay, so the Stern-Gerlach, I will again recommend you to please read this Stern-Gerlach experiment and Stern-Gerlach and spin concept. Another very important and a fantastic topic I can say to dig on. So in the Stern-Gerlach, I mean, you know that the Stern-Gerlach experiment was performed first time in 1922. And the major objective of the experiment was to prove that angular momentum is quantized. Okay. But during experiment, what they found, I mean, so they used the non-homogeneous magnetic field and use the silver atoms. And when they pass it through, and they found that the silver atom is going to split in two parts. So you're going to get two spots on the screen. So these two spots, of course, proves that the angular momentum is discrete. Space is quantized. Okay, but when they calculated the separation, okay, by using the FZ, okay, and they figure out that this. I will request everybody, please mute your mic if you are not asking question. So the other interpretation of this experiment was the spin. Okay, so when you calculate this fz and the separation, and from there you can actually calculate this ms value. Okay, and this ms value comes out to be a plus minus half, and this indicates that the spin, okay, the spin value is half, and the corresponding angular momentum, okay, you can calculate that is the SS plus 1 H cross. Okay, so the Stone-Gala experiment is very important, and we will try to spend some time on the Stone-Gala experiment, because with this one we will understand the spin in much better way. Okay, we will try to also look upon that the many students, when I interact with the students, they feel that when spin means something is spinning. Okay, so please now from if you already have this kind of wrong concept, then please try to remove from today onward. Spin doesn't means spinning. Okay, it is an intrinsic property of a system. We will try to understand what is the meaning of having spin half, what is the meaning of spin 3/2, and so on. Okay, so this is the one section where we will try to little bit spend some time. And in this spin, Stone-Garlock, I will also like to understand sequential Stone-Garlock. I mean,
No, I think there is one person who is, I don't know whether he's going to ask the questions, he's just muting and unmuting. Hello, Balaji, are you going to ask some questions? So, okay, I think there is no, I'll mute him. Again, he was unmuting. Okay, yeah, Sugam, please continue.
Sugam is muted. You can unmute Sugam.
yeah. Okay, so what you can do, you can write down some question in the chat box, maybe. That's the better way if you're facing some problem in the audio. So what I was trying to say that we will spend some time on this SG experiment, and then we will also understand the sequential Stone-Garlock. I mean, if I apply or combine more than one SG together in a different direction. I mean, when I say different direction, means a magnetic field in the different directions. So, okay, let us say in the first case, I can say Z direction, second also Z, maybe then X, then what is the outcome? So these sequence we will try to understand. This sequence is important because then here with this sequence, I will try to explain you what is the now how to write down the spin wave function, arbitrary spin wave function. Okay, when the spin is in the arbitrary direction, arbitrary spin direction means spin is not along the Z, X, or Y, but let us say somewhere in that plane, okay, in that space. And in that space, then I will explain you how to write down the operator. Okay, operator, of course, is going to be very simple. We will understand, we will spend some time here. It's going to be sine theta and cos phi plus so on like that. The interesting part for me here that this is the operator for a spin in a general direction. Let us say a direction called n. I mean, you know that when the spin is in the Z direction, okay, then corresponding operator, you can write like a h cut by 2, 1, 0, 0, minus 1. When the spin is in the x direction, you can write down the h cut is like a 0, 1, 1, 0, and so on. But what if the spin direction is along the n, some general direction. This is how you're going to write down the operator. I can write down the matrix form also. And this matrix, then from this matrix, I can find out the eigenvalues and eigenvectors. And here, this is what I want. Okay. So the general, when the spin is in some general direction, let us say n, then the general wave function, okay, of this we can write like cos theta by 2 into 0. I mean, this 0 means the state correspond to up and down, and plus e power what is happening? I phi, then sine. Mhm. Some issue with the board. Just give me 1 minute. Okay, it seems like there is some issue, but anyway, this is the what I want to now focus, that the wave function of the spin can be written in this way, and from there we will try to understand the blogosphere. Uh, can you see what I'm writing? Can you is it visible to on your screen, or because I'm facing some problem here?
Sir, it's visible but somewhat slow.
Very
Okay,
slow.
very slow.
It starts lacking.
Maybe let me switch off my video.
Still the same.
Okay, just give me a minute. Just give me a 2 minute break. I mean, I think I need to switch off and switch on the system. Is this fine?
Yeah, you could close this one itself and try once.
Okay. Okay, so I'm audible now.
Yes, you are audible.
Sir,
Sunil, can you allow me to
Yeah,
share, please?
yeah. Now I'm allowing you to share. Okay.
Okay, I think now it is working, you know?
Yeah, it looks like it is all right now.
Okay.
I have made you a co-host now. Okay, so
Mhm.
you can continue now.
I will just keep my video switched off. Okay, so what I was trying to emphasize here that we will focus on the wave function of the electrons spin, and with this one, I will try to explain you the blosphere. And actually, on this is a blosphere, and on the blosphere, actually, we can show some dimensions, y and x-axis, and on the surface of this blosphere, that is the spin direction. Okay, so that spin maybe along that direction I can call as 0, and along negative z direction I can call as 1, and so on. So this spin can take any orientation, okay, on this blosphere, and based upon this orientation, then I can write down the different now I can represent the different bits. So that is the one part which where we will spend some time. And after this, then the next topic, which is the uh, main, I can say, topic for us to understand, that is the from the quantum mechanics, we will go to the quantum computing concept and quantum gates. That is the fourth lecture, or maybe third lecture also can be, and quantum circuit also. So here I will let you understand the first of all, I think I will start with the basics of uh, computing, and there what is required is to understand the difference classical bits. So for example, when you're talking about the MOSFET, so this MOSFET is on and off. That is what is representing the two states of the classical system. And using these transistors, you can make gate, and using these gates, you can make different algorithms. Okay. For example, you can make a full adder. So combination of these gates will allow you to do some numerical calculations. Similar concept, but completely different fundamentals is the about the quantum bits. So in the quantum bits, then I will explain you that different platforms use different quantum bits. For example, electron spin, which is nothing but exist in up and down spin both. So I need a two-level system. Any two-level system can be used as a bit. Okay, so they can be used like a 0 and 1. So here, for example, it can be 0 or it can act like a 1. So any two-level system, so it can be electron spin. It can be for example, when talk about a hyperfine levels, so it can be F0 or F1. It can be a Zeeman levels, two Zeeman levels, maybe J equal to 0 or J equal to 1. Okay, so any two levels, okay, doesn't matter whether it is electron spin, is a hyperfine splitting or Zeeman splitting. Okay, any two levels can be used as a analogous to the 0 and 1. And but if we are using only this 1 and 0, two levels, okay, then this system is no longer different from the classical system. And this is where our the concept of the superposition going to help us, because these two basis states are definitely there, but there is another legitimate quantum state in the quantum mechanics, that is the superposition of these two basis states. For example, if you look back to our first this concept where I talk about this wave packet. So I told you that the psi x can be written like this way for a discrete system. Of course, for a continuous, we can put an integration. So this phi 1, phi 2, phi 3, they are called the basis states for n dimension. And here, for a 2-dimension or a 2-level system, I can write the superposition like a 0 and 1. So this is also a legitimate allowed state in the quantum mechanics. And this is the where you're going to see the supremacy of the quantum system. Because if you have only one electron, and this one electron is going to be in this state or in this state, or maybe a superposition of these two states, which is called this one. And in this state, you can see you have only one quantum bit. But to define this state, you have to define these two complex numbers. So to define a wave function of a single qubit in a superposition, you have to define these two complex number A and B. And this is where the quantum mechanics or quantum computing gets its supremacy. Because it means that this one wave function is going to have a two piece of informations, A and B. So so you have one qubit, and you can see that you need to have a 2 power 1 complex number to define this psi. If I have let's say 2 electrons, mean 2 qubits, then the 2 qubits, the wave function can written like let us say A 0 0 plus B 0 1 plus C 1 0 and D let us say 1 1. So it means that to define the superposition of 2 qubits, okay, you have to define these 4 complex numbers. So it means if you have 2 electrons, then 2 power 2 means 4 complex numbers are need to be defined. Similarly, if you have 3 qubits, 3 electrons, then you need to define 8 complex numbers. So you can see the amount of information that this wave function is carrying is enormous, is going as exponentially higher. And similarly, whereas in the classical system, if you have one transistor, it means it will going to have only 1 bit of information. If you have a 2 transistor, it will have 2 bit of information only. If you have a 3 transistor, it will have a 3 bit of informations. So here you can see if you have a let's say 300 transistors, then you have a 300 bit of information. But if you have a 300 qubits, the superposition of 300 qubit is going to store or going to store 2 power 300 information in form of these complex numbers, which is nearly equal to 10 to the power 90. And you can see, I mean, in our universe, you have, I think, less than 10 to the power 80 number of particles. Okay, so the amount of information that this wave function, the superposition of these 300 qubits carrying is enormous. Is much more than the number of particles in the universe exist. So this is the where the this quantum computer attracts people. And you can see that if you can create 300 entangled qubits, and entangle means you can create this superposition state, then there you will going to have this wave function going to have this much information. But of course, when I say this much information, doesn't mean these many numbers are stored. No. numbers are not stored this much. Informations are there 300 to the power 300, but when you're going to do a measurement, okay, only one number you're going to get, or maybe 300 numbers you're going to get out of this. So this is the where we will spend some time on these quantum qubits and how they are different from the classical qubits. And using these quantum qubits, we can make different gates. So we will focus on the quantum gates. That is our next topics in this lecture. So we will focus on the, let us say, a single qubit gate. So for example, the most popular quantum single qubit gates are like poly X gate, Y gate, Z gate, and so on. There are many. Okay. So I will not only discuss how to represent mathematically, but I will also try to let you understand how to create these qubits, okay, gates. So for example, when I say poly X gate, this poly X gate is similar like a classical NOT gate. Means classical NOT gate, what it does, it convert 0 to 1. Similarly here, when the electron is in the having a spin, let us say in the ground state, then if I apply a poly X gate, okay, so poly X gate apply on the 0, it's going to make it 1. I mean the particle going to flip its spin and going to go up spin. How it can be done? Easily you can see, if I shine some photon, which is exactly matching the energy, then this can make this transition. So we will see that how to make these gates by shining some photons, but a certain amount of time. So generally these qubits are realized maybe by shining laser light or maybe some microwave. For example, if we are using hyperfine or Gman levels as a qubits, then here we can shine some visible light, okay, in the, let's say, Gman level. Okay, so they can be used or maybe EM waves we can be used to make a transitions. But if you're using electron spin, then here we need microwaves in gigahertz frequency. So we will see that how physically we can produce these gates. So we will talk about single gates. We'll talk about a single qubit gate. We will talk about a 2 qubit gates. Now, see, understand, I told you that these two states, okay, are important, but the quantum supremacy comes when the wave function is actually written as a superposition of these two, okay? So a gate which do this job, that is actually called Hadamard gate. Hadamard gate or H gate. So when I apply H gate, okay, on this state on 0, then this is going to put this into a superposition of these two states. And how it can be done? Again, you can, I mean, I can give a small glimpse here. For example, I said that if I shine a photon, okay, for a certain time, then you can see that this probability of electron to go to up is become maximum here. After that, if I keep shining, then it will going to come down also. So it will again come back, again go up. So, but if I shine photon, let us say for this much time, so it is neither in the up state nor in the down state. So it will be somewhere in the superposition state. So if I shine the photon for a less time, and how much time it is, I will tell you, that is called the pi/2 pulse. So if I can shine the pi/2 pulse, then I can create a superposition state. And we need this superposition state because this is going to give the quantum supremacy. And the gate which does this is called Hadamard gate. And how we do it? By shining photons or by shining microwaves for a pi/2 time. This is the way we can discuss some more gate like a C0 gate. This is called the control NOT gate, another very important gate. Okay. We will talk about a swap gate. So this is going to swap the 2 qubits together. Control Z gate also. No. Similarly, we can think about 3-qubit gate also. For example, CC0 gate, or maybe this is also called Toffoli gate and Fredkin gate. So we will discuss this in detail and how to build them physically. So let us say if you have any platform, maybe superconducting qubits or let us say spin qubits or let us say hyperfine qubits, how physically we can make these gates. Okay, so this we can understand physically, and we will understand also what are the purpose of these gates. Particularly the C0 gate is very important, because I will tell you in detail later on that if I use hard mod and C0 in combination, then it will going to give me the entanglement. So if I want to create entanglement, so entanglement can be done by applying a hard mod gate and the C0 gate in sequence. So this is the about the gates, and we also discuss about the quantum circuit also. For example, how to apply a hard mod gate and C0 gate, maybe in series or maybe in parallel. So those things we will try to discuss in the quantum circuit. So this is the another topic, which is the maybe a third lecture, or maybe can be a fourth lecture also for us. So if anybody having any doubt up till here, please let me know.
Yeah, hello.
Yes.
Hello. Yeah, this may be a naive question. Actually, although qubit is entangled, but when we measure, of course, it is collapsed to one of the state, right?
Qubits are in superposition state, yes.
Yeah. So, so when we measure it, it collapsed to one of the states, right? So,
Exactly, yes.
does it pose any problem for the information retrieval?
Definitely, yeah, definitely, yes.
So, is that an issue as such?
This is not an issue, okay? Because what we will do, see, there is for example, when you try to do some quantum computation, for example, let us say if you want to add, let us say 2 plus 3 number, correct? And if you use, let us say a simple calculator, it will going to give you 5 number. But I can tell you, if you do this calculation through quantum computer, okay? So 2 plus 3, okay? The possible outcomes, I mean, if I use, let us say 2 qubits at the input, then I'm going to get output like 0, 1, 2, 3, 4, 5, 6, and 7. If I use the 4 qubits at the input to initialize, it depends. I mean, for example, if I'm writing 2 qubits or maybe these two, for example, these two written like a 0, 1 and 1, 1. Okay, or maybe I can use 4 qubits. So in 4 qubits also I can represent the same number like this. But in this case, the possible outcomes will be 0 to 16. So this is the superposition. Okay. So in superposition, these are the possible results you may expect, correct? So, but what we do that we do interference. And this I will explain you in detail.
Okay.
So we do interference, and the interference, what we do, we write algorithm in such a way that the superposition corresponding to 5, okay, this is going to have a positive phase, and other wave function going to have a negative phase. And when they're going to again add up, then this 5 result will going to amplify, other results will going to destructive interference, and they will go down. And the probability, you can see that the probability of maybe this is 1, 2, 3, 4, and probability of 5 will be higher.
I see.
And after that, you do measurement. Okay, so this is still in the superposition state. But now you can see when I say superposition means, let us say result 1 have some probability, result 2 have some probability, result 3 have some probability, and result 5 also have some probability. But if now I do a measurement, okay, on this wave function, the wave function will collapse, but the probability of collapsing in the 5 will be highest.
Okay, yeah.
So this will collapse in the state 5, and then it is going to give 5. Maybe the 99% probability that that it will collapse into 5. So when you do the measurement, you will get result 5 output.
Okay.
So superposition still exists, but through interference, we have to enhance the result of the right result.
I
Okay.
see. Okay. Yeah.
If
So
the probability of the all are same, then is no longer useful, because when you're going to do the measurement, it will collapse in any of them with the equal probability.
right, right.
So
Okay, thank you.
superposition is very useful, because this allows you to do the calculation in a single shot with all possible results. And here interference will going to enhance the probability of the right result, and then the measurement give the output. We will discuss this. I mean, I will come to the algorithm. Okay, so we will discuss how these actually works.
There are 2 more questions.
Yes. Can you please read? Because
Okay. Sagar from JNU asks, other than electron qubit, is there any other quantum bit?
yes. I'm coming to that part. Okay.
And the other question is, information entropy increases during measurement? Question mark. This is from Surya Prasant S.
Information.
Information entropy increases during measurement. Does the information entropy increase during measurement? Maybe he can ask, try to explain what he was asking if you are not getting that.
Yeah.
Or he can write you an email later.
Okay. So after this, then we will come to the second part or fifth lecture.
Hello. I want to ask something.
Mm-hmm.
You just said that through interference we will increase the probability of our desired answer.
Exactly. Yes.
Okay. So we will construct our algorithm such that will happen.
That will happen. Yes, that's true.
But still, we have the non-zero probability of getting some wrong answers in each steps.
It will always remain there. Yes.
Okay. So doesn't for a complex calculation, doesn't it throw false positive often?
Yes, it will give you, but something is better than nothing. I mean, calculation which you cannot do with the classical calculators or computing system, you can afford to do with the quantum system. But yes, it will have this problem. Your quantum algorithm may need to be very smart, so that the probability of the right result become higher and higher. But yes, the problem you are asking, yes, it will be a part of the quantum computing system. You cannot make it 100% deterministic.
Okay. Okay. Now, for a multi-step problem, let's say I have several number of steps through some calculations. So it will become very quite challenging, I guess. I am not sure. I mean, if you have each step in a probability of 1% error, then the errors will can add up, and you cannot detect which step the error is coming from, and so on. And the final output will be something else. What you are expecting?
I mean, don't know. I mean, even the present companies also, like IBM and others, I know they're not unable to do or demonstrate some outcomes. Okay. If you look at the concept of the quantum mechanics, yes, it will remain a problem. Okay.
Okay.
And it all depends how your algorithm, how much it increase the probability. If you can go 90%, then maybe even if the calculations are in the steps, or maybe thousands or millions of steps, maybe still you can manage to get the correct answer at the end. But I mean, so if I say I'm not unable to tell you exactly how it will be now in the future.
Okay. Thank you.
Then the fifth lecture will be then this algorithm. So here, of course, I will like to first focus more on the quantum Oops. Oops, again, same problem.
It's not lagging, I think. I can see the thing moving fast.
Okay. So in here, then I will focus on quantum parallelism. And already we have talked about more. For example, when I say creating a superposition, this is what is called the quantum parallelism. So for example, I said that 2 plus 3, when you're going to add, okay, so it can create a all possible result at the simultaneously, and then you can get one result out at the output by interference and then measurement. So little bit we work on the quantum parallelism, and then we will come to the actual algorithm. For example, we will spend some time on the very first quantum algorithm called the Deutsch algorithm. So this has no practical use, no, but this actually tells you that why the quantum computers are superior. So this will let you know that if a function, okay, whether this function is a constant or balanced. Constant means if I put value 0 or 1 in the function, the value remain always same because it's a constant. But if I put, let us say 0 and put 1, then the values are different because this is balanced. So this is the meaning of the constant function or a balanced function. So Deutsch algorithm actually tells you when you do the computation quantum mechanically, let us say if you do classically, then you have to put first, there are two steps. Step number 1, you put value 0 and you will get something. Then put next step is you put 1, then you will get something. So there, in the classical system, there are two steps. Then only you will be able to tell whether the function is a constant or a balanced. But in the quantum algorithm, when you make a quantum algorithm, so in the quantum algorithm, a single step will tell you that whether the function is a constant or a balanced. But how it is done, this is the will take some time to explain you. Okay, so I mean here again the same things we will see. We will going to create a superposition, and then we're going to create interference, and that interference, maybe I can take example of the real interference of the two double slit and interference taking place in the Deutsch algorithm. Then I think you will be able to make a proper analogy between these two systems, and then how this interference going to increase the probability of the right result. So this is the algorithm I would like to discuss in detail. Then we will also discuss about Shor algorithm. So this Shor algorithm actually gives the prime factor of large numbers. So I mean small numbers, if you have, let us say, 1,000 or 100, so you know that this is going to be a 10 into 10 means 2 into 5 power square. So 2 square into 5 square. So this is the prime factors. But let us say if you have some large numbers, something, then maybe a classical computer take long time. And in the Shor algorithm, we will see the amount of steps required, okay, in the quantum system is less than the classical system. Similarly, we will spend some time on the Grover algorithm. And this is actually will tell you that how to search a number from a large database. So let us say if you want to find name of a person from a directory, then you will see that the number of number of data points are n. Then the classical system on worst side, maybe it is lucky that it can get the exact number maybe less than n, but on the worst side it will take n steps. Whereas a quantum system can do this finding, okay, or search in root n time. So it will take only root n steps to do the calculations. So we will spend some time on these quantum algorithms. And after that, we will go to the actual quantum computer. So the 6th lecture will be in the quantum hardware. And here, of course, you will find more interest because we will come in the lab actually. So up till here, we will be on the paper in everything goes in the mind and through mathematics calculations, but here in the quantum hardware and how to realize them. So there we will understand how to make these quantum computers. So first of all, I will explain you, there is some criteria that is called the Vincenzo criteria. I mean, if you want to make a quantum computer, then your platform must follow 5 criteria given by the D. Vincenzo. Okay, and these criteria include like your system must have a scalability. Scalability means if you have a 2 qubits with the some decoherence time, then this system should have the capability to increase to a large number of qubits without influencing too much on the decoherence time. So scalability must be there. I mean, scalability means your system should be have a capability to increase the qubits from, let us say, 1 to let us say 100 or thousands without compromising too much on the decoherence time. This is the first criteria. The second, that your system must should have the capability to initialize. So qubit initialization, this is another criteria required. It means you have a 2-level system. So let us say this is a 1 qubit, another qubit also have a 2-level system. Then I will start all the electrons in the ground state. So in the initial, maybe some electrons may be in the spin down, some may be in the spin up. Then I must start every system in the ground state. This is called the initialization. So, and this can be done with the poly X gate. So that capability your system must have. Then of course, this must have a long coherence time. Your system must have a long coherence time. So when I say coherence time means how long the qubit still remains in the superposition state. So for example, your qubit is A and B, 0 and 1 state. And because this qubit interacting with the electromagnetic radiation or thermal radiations, and because of this superposition is destroyed, and then the system is no longer in superposition, means based upon the superposition, you have made all the gates. And those gates are used to do the calculations. So if the system is no longer in the superposition, the gate is no longer reliable. So for example, different system has a difference. This is called the coherence time. I mean, for how longer time the system still remains in the superposition state. For example, superconducting system, their coherence time is 10 to the power minus 6 second only. It means that on an average, after this time, the superposition going to be destroyed because of the interaction of the qubits with the electromagnetic radiation, maybe thermal radiation, or maybe the surrounding matrices. It means you have to complete your all quantum mechanical calculation within that time. But if some system, let us say, have a better time, coherence time, then definitely you get more flexibility, okay, because this is the time in which you have to do the calculations, okay. So system must have a long coherence time. The coherence time must be greater than the gate operation time. The third one. The fourth one means your system, you must have a large number of qubits or gates so that you can make a universal quantum gates. And also your system must have a capability to have a qubit specific measurement. When I say qubit specific measurements, it simply means that you have large number of qubits So I want to measure the state of this one, then I should be able to measure this one without disturbing the other qubits. Or maybe I want to measure 1 and 2, 4, then I should have capability to measure 1 and 4 without disturbing 2 and 3. That is called qubit specific measurement. So this is the DiVincenzo criteria. So if you want to make a quantum computer, then your quantum platform must have these 5 capabilities. Then only you will be able to make a better quantum platform to make a quantum computer. So there are different platforms. So the second part in this, I will discuss about types of qubits, types of qubit across different platform. So for example, the first platform will be the superconducting. This is the most common platform I can say people using superconducting qubits. So I mean the physics we will discuss in detail, but simply I can tell you that in the superconductor, when you take a, let us say any wire or superconducting wire, a loop, okay, and then place in the magnetic field and then cool it down. So when you're going to cool it down, okay, then some flux is going to be trapped. So magnetic flux is going to be trapped inside, okay, because of Meissner effect. And this flux is maintained because of the persistence current that is flowing in the tube, okay. So this persistence current is going to flow, okay. And you will see that I will explain you that this persistence current is going to flow in a not in a one cycle, but actually is going to have this motion, okay. So this whole system is going to act like a LC oscillator. So we will come to the physics of this superconducting, and this oscillator is going to then act is like a potential is going to like a harmonic oscillator, and this is going to have a different quantum states, okay. And now these quantum states can be used to make can be used as a qubits, okay. So we can create a superposition of these qubits. So we will see that this superconducting qubit, this is how we can make a qubits. We will discuss the complete physics of the these qubits. So there are different types of qubits one can generate. So for example, the one category is called charge qubit, or sometime we called Cooper pair box. Another type of qubits are called flux qubit. Third is called phase qubit. I mean, these 3 categories are used. Either you can use the charge, I mean, you can use the Cooper pairs, okay. So if Cooper pair is there or not there, okay, so they can act like a state 0 and 1. You can use a flux, okay. Flux is quantized, okay, in the superconductor. You can use those, okay. Phase of the Josephson junctions, okay, those can be used as the qubits. And then there are modifications of this one. So one is called a transmon, okay. So transmon is actually a charge qubit. Most of the superconducting companies at these days, actually they are using these transmons qubits, okay. So transmons qubits are nothing but a improved charge qubit, where the Josephson's energy, which I will discuss later on, is much higher than the charging energy of the capacitor. And this is a going to have a much higher now flexibility when you talk about sensitivity toward the charge noise. So what is this is I will discuss in detail, okay. But keep in mind that the company like IBM, okay, or Google, okay, they are making their qubit using the transmons. So transmons are nothing but an advanced version of the charge qubit. So there are many others also, like Xmon, there is called Fluxonium, okay, various, I mean, I will discuss in detail when I come to these qubits. Similarly, there is second platform. This is a superconducting qubits. Another qubits platform is called trapped ion qubit. So see, there are two types of ion trap. So one is called a Paul trap, and there is called a Penning trap. So these ions can be trapped. So when, let us say, if you trap a calcium ion in the Paul trap, then the electronic states of the calcium can be used as a qubit. And then you can make a transitions in these electronic energy levels. So Paul trap can be used. So there are, I mean, different types of levels you can use. For example, if you're using the Gman levels, okay, so Gman's level corresponding we call as the optical qubits. You can use the hyperfine level, so we can call as the hyperfine qubits. We can call Gman levels, so we can call Gman qubits. So these are the possibilities, no, in the Paul trap. In Penning trap, we will talk about these things also, but the best possible is to use the electron spin qubit. So electron spin means these two states, spin up and spin down. So we can trap Penning electron in the trap, and we can utilize this spin up and spin down as qubits. And this is the portion where I am working. Okay, this is the portion for the interest in our institute also. So we will discuss about this trapped ion. Other than that, there are other platforms also. For example, photonics, qubits. So in photonics qubits, I mean, so you can use photon polarization, maybe. Okay, so you can see, just a minute. Yeah. So you can use the polarization of the photons. So we can call polarization qubit. So you can use, let us say, horizontal polarization or vertical polarization. They act like a two qubits. Even you can use the path qubit. Means there are two, let us say, optical fibers, and you shine photons, one single photon. So it can go in this or in this, you never know. So they can be in the superposition. So which path photon is going? So these two paths can be used. So path one or path maybe A or path maybe B. So they can be used as the qubits. Other possibility like time qubit also. So in the time qubits, you use the you can encode a quantum information in the time of arrival of the photon. So maybe you can say early photon or late photon. So they can be used as the qubits. Even you can use the frequency also of the photons. So that is called the frequency qubit. So you can use the different frequency modes. No, so here you can use the frequency mode of photons as a qubits. Okay, so one mode may be called one, other mode can be two. So they are the third platform. And the advantage of these photons qubits are numerous, because they don't need cooling. We will see that in the superconducting qubit and the trapped ion qubits, we need to cool down the whole system below 100 millikelvin. And that required a good amount of investment. Whereas in the photonic qubits, no such investment is required, because we don't need a cooling for this one. They can work on the room temperature. But producing these qubits and sustaining them is more challenging in comparison to the electrons or the ions, which you can trap in a particular fixed location. Then the fourth platform can be like a neutral atom qubit. So in the neutral atom qubits means you can trap neutral atoms also. For example, rubidium and cesium, these are the most studied atoms. So you use the magnetic moment of these ions to trap. Okay. So, but once they're trapped, so their energy levels can be used. So, for example, you can use the hyperfine level of this rubidium and cesium, and corresponding the qubit is called the hyperfine qubit. And those states you can use, let us say f equal to 1 or f equal to 2. These two states can be used as the qubits. So all the atoms, rubidium, cesium trapped, they can be give this flexibility. Or you can also use the Rydberg states, and accordingly we can call as the Rydberg qubits. Rydberg qubits means in this case you can use the one state as the ground state. So you can use the ground state and one highly excited state or highly excited Rydberg state of neutral atom. So these two states can be used to make the qubit. I mean, here then you need a strong dipole-dipole interaction to make the these gates faster. So similarly, another platform is like a topological qubits. So topological, in this one, the most popular and these days is very in news also, that is called the Majorana. Majorana qubit. So Majorana was a scientist, so he developed this concept. So we'll talk about briefly about the Majorana qubits and also about Ennean qubit. So recently, I think Microsoft they came up now with the idea. They have not be careful. They have not made this Majorana qubits yet. They have come up with a proposal that they can make millions of qubits using the Majoranas. And so I mean the Microsoft, that is a company making this one. So I think I must tell you other companies. For example, when you talk about trapped ion qubits, so there is an IonQ company. IonQ company, a US-based company. They have already made this ion qubit, and of course I told you the superconducting is already done by the IBM and the Google. So these two are the another one topological. They're called topological qubits, and another is maybe we can call quantum dots. And silicon based. So here, I mean, so you can use electron spin qubit. It is same like in ion trap also. You can utilize the electron spin as a qubit. Even you can use the whole spin as a qubit, or you can use a donor qubit. So here you can use the spin of a donor atom. For example, donor atom like phosphorus in silicon. So what do you do that you simply you have a, let us say a source, and then you have a drain and gate. So you can just implant one phosphorus atom. Okay. So you can use a single ion implanter to implant a phosphorus, and its electron, the fifth electron, you can utilize as a qubit. So we will talk a bit about this also. So these are the possible 6 types of platforms at the present are popular. And keep in mind that none of these platforms are, I can say, has proved that they are superior. I mean, they are the ultimate solution. Still, there can be different platforms can come up. because each and every platform has a challenges. So the last lecture will be the challenges. Challenges in the hardware. There's no challenge in the software, but challenges are there in the hardware. And the major hardware issue, if we talk about, is the decoherence. So we will talk about a decoherence. I think by the time I will come to this topic, you might already having the concept of decoherence in detail. I told you that for how long the electrons remain in the coherent state or in the superposition state. That is called the decoherence time. So as you mentioned that superconducting material, okay, they have a 10⁻⁻⁶ decoherence time, whereas the ion trap, they are much more superior in comparison. They can have a few seconds or few minutes also. So we will see why the decoherence comes into picture. Then we'll talk about a noise. So noise means physical system like superconducting circuits or trapped ions. They are always going to have a interaction with the EM waves. They're going to have interaction with the neighboring magnetic field produced maybe because of the nuclear magnetic moment or the neighboring electrons. Thermal fluctuations are there. So these are the noise which is going to cause this wave function to collapse. So this is the issue we will talk about and how to tackle these noise. Then the other issue is scalability. This is the biggest issue at the moment. I mean, people are able to make maybe 10 qubits with some decoherence time. But when they are trying to make it 100 or trying to make it 1000, the decoherence time is no longer remain the same. It is increases. Okay. It means the amount of time you have to perform the calculations is less now. So the scalability is the biggest issue at the moment in the quantum computing business. And another challenge is that, for example, when you talk about noise, so this noise is going to, let us say electron is in the spin up and spin down, and you have created this system, and because of some kind of interaction, the spin flips by itself. Okay, then how to now manage this one? And this is done by a very fantastic concept in the quantum computing that is called the quantum error correction. So I will discuss this in detail. Okay, we will spend some time to understand what is the quantum error correction, because this gives us some amount of liberty. Okay, so if even one qubit gone bad because of the interaction with the electromagnetic field or magnetic field, still, if I have a spare qubits acting as a ancilia or no, as a spare qubits, so those spare qubits I can use to restore the information back. And how we will do it, I will discuss when I will come to the quantum error corrections. Okay, so this is a very important part, because with this one, we manage, even if some qubits gone bad, still we can reconstruct the information back. Remember that in the quantum system, you cannot copy the information, no cloning theorem. You cannot make a copy, and you cannot make a large number of copies. So once the information is gone, is gone. Okay, only information can be reconstructed with the help of the another qubit. So those qubits, extra qubits, which is called ancilla qubits. Okay, and those qubits use to reproduce the information, and those part is called as the quantum error correction. This is mathematics we will try to understand. I will give some example, and for example, in Dutch algorithm, I will see how this quantum error correction works. So physically we will run the system, we will see. So this is the one part. which we will discuss, and maybe on the last day itself, we will try to also look on the possible different companies which are in the pictures. For example, IBM, so more famous, Google, what they have, okay, INQ. So they are having a running quantum computer, but what are the limitations they are facing? We will try to focus on these parts. And particularly, I will also, if I get a time, then we will try to run, okay, some program, okay, using the IBM Qiskit. So please, I will recommend everybody, please try to install this Qiskit and try to read about it. Maybe when I will discuss the algorithm like Deutsch algorithm or Schur algorithm, so maybe those algorithm I can run on the Qiskit. Okay, if at that time, if we get the availability, means it's not necessary that we will get the availability, but maybe I can record this video and I can show you separately if I don't get the time to run this system online. But even you can try yourself and get some familiarity with the Qiskit, and we will see how to make different quantum circuit, how to run different existing quantum algorithm like Deutsch, Grover, and Schur algorithm using the Qiskits. So we will try to do some practical also. So objective here is that we will start from the scratch, from the fundamental of quantum mechanics, and we will come to running the Qiskit also. And objective here is to encourage the young students to choose their career in this field. And once they find this subject fascinating, definitely they're going to choose their research career in this field. Okay, and my personal objective will be to make you confident now after this 16 hour of class, feel confident to jump into any platform. If you want to do research in the superconducting qubits, you should have that capability. If you want to go into the ion trap, you should have the capability to do that part. If you want to jump into the photonic, you should have that confidence. So that is my objective. Okay, and hope that we will be able to now manage this part by the end of now 16 hour of our lecture series. So that's all from my side. And if you have any questions or any suggestion, if you want to give, you are welcome.
Okay, thank you, Sugam. So now, if any of you have any specific questions, so please feel free to ask.
So I hope everybody got some now holistic idea what we are going to discuss, okay, and what this system is all about. So this content in the first class, I just kept deliberately in this way so that you get the whole complete picture in your mind. And then I think you will manage to keep your enthu throughout the session. Yes, somebody was asking something.
So thank you for the outline, sir. Sir, I was asking about that DiVincenzo's criteria. So
Yeah.
among the five that you mentioned about that universal quantum gates, right? So is it necessary to have universal quantum gates, and what is the logic behind it? If we see classically, then we have universal gate called NAND. So using one NAND type gates, you can build any type of gates you need.
So there is no single universal gate in the quantum mechanics. Okay.
Yes.
Yeah. So we need some sets of some single qubit and 2 qubits system or 3 qubits to make a so that you can do all possible operations. Okay.
Okay.
So, but the answer is that there's no single qubit or single gate which can act as a universal gate in the quantum system. You need set of 1 qubit and 2 qubits gates which can which are collectively use to create any kind of computation.
Okay, thank you. And is there any other kind of WhatsApp group or chats where we can place our queries in?
I think that is a good suggestion. Maybe. Okay, what I can do, I can make one WhatsApp group and I can just share a link, and you all can just click that link and join that WhatsApp group. And there we can have more discussion offline also.
Okay, sure.
Sunil, how we can do it? Maybe I can send you
Yeah.
the WhatsApp and you can send everybody, right, through mail, and they can just click and join that group.
Yes, yes, that's right. Yeah, I think yeah, I can also do one another thing. Like I have the list of registered participants.
You can do it. Yes, it will be better.
Yeah, so there I can actually send this to everyone. So you generate a WhatsApp group, and then you can share the link to join the WhatsApp group.
Yes.
And then we can also I can share it with all the registered participants so that they can I'll join that group. I hope that will be good enough. There
Good
was
idea,
actually
actually.
one question. Yeah, that can be done. So another thing is that there was a question regarding the textbook, a standard textbook regarding a quantum circuits, or any reference to read about it in detail. So this is from Srinath Mukherjee.
I will send you now on the WhatsApp group.
Yes, so I think all these questions can be asked in the WhatsApp group, and we can start doing that. So I will. So you can expect an email as a reply to all the same.
Maybe in next 30 minutes. Yes.
Yeah. In the next time, I will send you that. After Sugam shares me that link to the join the WhatsApp group, I will share it with everyone who has registered.
Sir.
Yes.
Sir, the systems which you have described for realizing the qubits, most of them are, I mean, two state systems, right?
Yeah, maybe
Do
can you also introduce
you?
Like you can also say your name and then maybe ask questions.
Okay, sir. I am Siddharth Sharma from Dr. B.R. Ambedkar University, Agra.
Yeah.
Yes, please.
So for physically realizing the qubits, well, you have described the system with two states, right?
Yeah.
So do we have, because I have seen earlier, because you have said about oscillator, harmonic oscillator, it has multiple states possible, right?
Yes.
So can we have more than two state system as a qubit?
Well, no, we need a two state system only. But in a system where you have a multiple levels, okay, they will cause problem. Okay. So the problem is that if they are, let us say, equally spaced. Okay. So see, what I'm trying to say that the system act like qubits. Okay, qubits means up state and the down state. So to do the quantum this calculation, you need two states. Okay, so you have to stick to the two states. And but here in the harmonic oscillator, when you have multiple states like 0, 1, 2, and 3, and so on, and they are equally spaced, and in principle, any two states can be used. But let us say if I'm going to use, let us say, this and this as a qubit states, then initialization is going to be very difficult. For example, you're going to cool down the system and you want to ensure that all the qubits are in this state. So that is not going to be possible. Okay, so to make sure that initialization takes place, what we do, first of all, we go with the lowest quantum states, so that when you're going to cool down to a very low temperature, then all the ions or all the qubits will be in the ground state. And the second, when you're going to excite, okay, So the excitation should not cause any this transition. This should cause only this transition. And for this one, what we do, generally we make a n harmonic oscillator so that these gaps are different. So when the gaps are different, then when you go do a shine of photons, so this photon energy is correspond to this much. So this can cause only this transition. This will never going to cause this transition or this transition. So this way, I will ensure that only these two states are used. So answer to your question that you have to use only two states, and in the multi-level system, you have to make some changes, okay, so that the system become n-harmonic. And in the superconducting system, this is done by introducing n-harmonicity by introducing a Josephson junction.
Okay.
So Josephson junction actually cause another energy in the potential energy, which is linear in term. Generally, potential energy is x square, and that is going to make a parabolic. If somehow you add some beta x, okay, or maybe higher order terms, then this is going to cause an harmonicity. And this is what is done by introducing Josephson junction in the circuit. That is going to introduce non-linear terms, okay? And that cause this splitting unequal and make us reliable to use these two levels.
Okay, thank you, sir.
Anybody else?
Okay, I think it seems that there are no further questions also in the chat. So I think we can conclude it for today.
Okay, good. Then
okay.
what
One
we
more thing. I think for the participants, I have seen that some of them are annotating on the page. I would request you to annotate from your side, or make noise. I mean, make sure that your speaker, like your microphone, is muted when when you have stopped asking questions, so that there is no disturbance in the class. This has been happening, unfortunately, today. I hope the next time everyone will take care of this. Okay, yeah, Sugam, thank you very much for the very interesting and like, very great introduction to quantum computing. And I think this will continue, and students will be benefiting from this course more. And for this WhatsApp group, please share that link, and I
yes.
can send this around to everyone.
Yes.
Hello.
So
Any
tomorrow
other
we're going
questions?
to tomorrow we're going to discuss two topics. One is the overview, I mean some historical development, and second I will discuss about the quantum mechanics fundamentals. So these two topics we will be discussing tomorrow. Yes, I think somebody was asking question.
Yeah, somebody started asking. Yeah.
Good evening, sir.
Yes.
Sir, my name is Dr. Nirbhay Singh. I am sir presently working in MIT. So I have no question up to now because I have also attended some previous lecture of yours. So I would just want to say thank you so much, sir. It's second time I am getting this lecture and involved in learning through your lectures. Thank you so
very
much.
much. Thank you.
Thank you, sir.
Okay, so we will make this whole 8 or 9 days objective is to make it very interactive, and let us try to learn. You learn
Yes.
from me and I learn from you, and your questions will push me to read more and learn more.
Yes, sir.
So
Sir, one
please,
thing I
please
want
ask
to ask.
questions as much as you can do.
Yes.
Yep.
Sir, can we get the PDF note type for daily lectures?
Yes, I will provide you.
Yes, sir.
In the
Thank you so much.
WhatsApp group, I will provide you the notes also. Yep.
Thank you so much, sir. Thank you, sir.
Okay.
Okay.
So
So
shall we now conclude it?
I think yes, I think we can do it, and we will.
Okay. So then we will meet tomorrow at 6 p.m. sharp at 6 p.m. Okay. Yeah. Thank you everyone for joining, and see you tomorrow.
Yeah. See you then.